When an industrial motor fails on an assembly line, the costs multiply by the minute. Factories lose millions of dollars a year to broken parts and unexpected downtime when a critical piece of machinery grinds to a sudden halt. But we can prevent those failures before they happen. Today, we are going to build a custom IoT smart motor system from scratch, using an ESP32 microcontroller to monitor our hardware in real time. We will wire our motor with current and temperature sensors, connect it to a cloud dashboard for live tracking, and program an automated safety kill switch that triggers the moment something goes wrong. This miniature setup exactly mirrors the predictive maintenance workflows used across modern smart factories to extend hardware lifespan and keep production moving. Before we wire anything, we need to map out our blueprint. Industrial IoT systems rely on a standard 3-layer architecture to handle the flow of information. This diagram outlines our infrastructure. At the bottom is the device layer, our physical hardware, ESP32, motor, and sensors gathering data. Moving right, data travels through the network layer via HTTP or MQTT gateways, finally reaching the application layer to populate our cloud dashboard. Mapping this data flow visually is step 1. It takes isolated, standalone machines and links them into an intelligent, communicative network. Let's build the device layer. We wire an ACS712 current sensor and temperature sensor into the analog input pins of our microcontroller. These metrics are the motor's vital signs. High current means mechanical parts are binding, while high temperature points to dangerous friction. Now, a critical safety note. You must supply power to your motor separately from the ESP32's logic power. Drawing heavy motor current straight through the microcontroller will fry your board instantly. Properly isolating those power sources and wiring the sensors creates the physical foundation we need to capture accurate digital measurements. With the hardware wired, we need to give it some instructions. Instead of relying on the cloud, we write local logic directly onto the ESP32. This is called edge computing. We program simple if-else rules into our Arduino code. If the current exceeds 6.0 amps or the temperature rises above 50 degrees Celsius, the system automatically cuts power. Processing this data locally means the system can trigger an instantaneous safety shutdown. It doesn't have to wait for a signal to travel to the internet and back, avoiding network latency that could cost us the hardware. This binary threshold acts as a hard limit. In advanced setups, machine learning is layered over this to observe subtle trends, predicting a failure days before limits are ever hit. So edge computing provides the immediate reflex to protect the asset right now, while the cloud handles the long-term memory. Let's build that long-term memory. By adding local Wi-Fi credentials to the code, the ESP32 can push the sensor readings straight to a cloud dashboard, like ThingSpeak. How you send that data matters. For simple, infrequent updates, the HTTP protocol works perfectly fine. If you are streaming continuous, high-speed industrial data, MQTT is a much more efficient choice. This chart shows our application layer in action. As raw data flows in, metrics plot onto a live line graph, tracking how the motor behaves under normal conditions, and immediately seeing when a sharp upward spike crosses our danger threshold. Establishing this connection completes the architecture. What started as a local kill switch is now a globally monitorable asset. Let's test the entire system. Power the setup on and let the motor spin up, and then carefully apply physical resistance to the shaft to simulate a heavy load failure. Watch the metrics. As the motor struggles against the resistance, the current spikes on the dashboard. The ESP32 instantly recognizes that the 6.0 amp local threshold has been breached, and it kills the power, saving the motor. This physical test is the baseline for large-scale manufacturing. Smart factories feed continuous streams of real-time data into sophisticated AI models. By analyzing operational history, the AI dynamically adjusts motor speeds based on actual load conditions, rather than running blindly at maximum capacity. That automated analysis pulls double duty. It protects the machinery from failure and actively optimizes energy consumption across the entire factory floor. You now have a fully functional prototype. You've built a complete 3-layer IoT monitoring system equipped with edge control safety logic. Zooming out, this is the core of predictive maintenance. Catching minor wear and tear by detecting anomalies early saves industrial plants millions in downtime and significantly extends the lifespan of their hardware. Your next step is to level this up. Try exporting your historical cloud data and using it to train a simple machine learning model to recognize the specific vibration patterns of a failing bearing. Gathering the data is only the beginning. The true value of an industrial IoT network lies in turning those numbers into autonomous, protective action.